Hey yo, what is going on? It's your boy, and today we're going to be going over one of the three types of proofs. This proof is what we call proof by contradiction. And so this type of proof works by doing a couple things. First, it works by assuming an implication is false, and it works also by using theories and axioms to arrive at a contradiction. So theories and axioms to arrive at a contradiction. By doing this, you're proving that the original statement must be true because the implication of it being false doesn't work. Let's do a pretty easy example. Let's say if integer n is odd, then n squared is also odd. So based on what we listed out here, our first step is to assume the implication made is false. So we're going to assume that n squared is even. So assume n squared is even. We're assuming the opposite. So that would mean n squared equals 2k, because any even number has or includes a factor of 2. Oops. Pretty much, we can also write n squared as n times n, which is also equal to 2k. But, as you can see, this can't be true. Oh, my friend. We assume n is odd, but we can see that the product of two odd numbers can't be even. So that doesn't work out. So we say that because the product of two even numbers equals an even product, this statement contradicts itself, which means it's wrong. Another more complicated example is something like this. So let's try and prove that there's no x value which belongs to the set of real numbers such that 1 over x minus 2 equals 1 minus x. So again, our first step is to assume the implication being made in this question is wrong. Let's assume that there is an x value which belongs to the set of real numbers such that 1 over x minus 2 is equal to 1x. And let's call that x value a. And so we can substitute for x. And by assuming this, let's work it out. So what you can do is by the rules, by the equality rule, where the product of the mean equals the product of the extremes, you can say that 1 is equal to the product of 1 minus a times a minus 2. And so this would be 1 equals a minus 2 minus a squared plus 2a, which reduces into negative a squared plus 3a minus 2. And if we set this equation equal to 0, we get negative a squared plus 3a minus 3. To evaluate for a, we can use the quadratic equation, where a is equal to 3 plus or minus the square root of our discriminant, which is negative b, which should be negative b, plus or minus the square root of b squared minus 4ac over 2a. So that would be 9 minus 12 over 2. But notice, our discriminant, denoted by this weird triangle, is actually less than 0. And because we can't take the square root of a negative number, there is no solution that exists for a, so we just contradicted ourselves. When we do say that there is an x value that belongs to the real number set that makes this statement true, we find a contradiction. And so this can't be true. One really famous contradiction that we can make to prove something was developed by Euclid's theorem of infinite primes. And what he did is he suggested, or he made an implication, that there weren't infinite primes. In other words, there were finite numbers of primes. In other words, I can quantify the amount of prime numbers that exist by listing them in a set. So I could say that the amount of prime numbers could be included in the set from P1, P2, P3, all the way to Pn. And because I have a Pn, I'm saying that at this Pn value, that's my last prime number. There's no prime number that exceeds it. What Euclid did is that he called alpha, and he said alpha was, well, it was the product of all these prime numbers. It was a product of all these prime numbers up to Pn, but then he added 1. And so by doing this, he proved that alpha divided by any prime number always resulted in a remainder of 1. So in this instance, he proved that, alpha can't be divided by any primes. So alpha cannot be divided wholly or completely by any prime number. But this is actually a contradiction, because the fundamental theorem suggests that any number can be broken up into a product of 2 or more prime numbers. And you've actually explored this before, because maybe you've done something like a factoring tree, and a factor tree breaks down a number into all its simplest factors. And every natural number greater than 1 can be broken down into a product of 2 or more prime numbers. So the fundamental theorem states that a number, at least a natural number greater than 1, can be broken down into a product of 2 or more primes. But here we say that alpha can't be divided by any primes, which suggests that alpha can't be written as a product of two or more primes. So by saying that, we're saying that alpha in and of itself is a prime number. We're saying that alpha in and of itself is a prime number. And that contradicts the idea that there are finite numbers of prime, because now we have a prime number that we didn't include in our finite set, which suggests that there are an infinite number of prime. So I hope that helped. I'll also be posting a bit more videos on other proofs, like direct proofs, proof by counterexample, and proof by induction in other videos. But hopefully that helped a bit. And yeah.